So hello friends, I'm here to present you op-amp as inverting amplifier with feedback. So let's start with our video lecture, the application of op-amp, how we can use op-amp as inverting amplifier. So the diagram represents operational amplifier that is connected in inverting configuration with feedback. As you can see from this diagram, the positive terminal of op-amp is kept at ground potential, that is 0 volt, and negative terminal of op-amp is connected to input supply, that is Vin. So that's why it is referred as a inverting configuration. That is, inverting terminal is connected to Vin and non-inverting terminal is kept at ground potential. Another point, there is a resistance, feedback resistance, that is RF, which connects the output back to the input, that is inverting input of the op-amp. So in this case, the input voltage drives the inverting terminal, and the amplified as well as inverted output signal is also applied to inverting input via feedback resistance. So at inverting terminal, there are two types of signals. One is input signal, another one is the feedback signal. So in this arrangement, the negative feedback is there because any increase in the output signal results in feedback signal to inverting input. If there is any increase in the output signal, then there will be a feedback to its inverting terminal. That's why the output signal will decrease, and hence the feedback is negative. Now we can analyze the given circuit diagram with the help of Kirchhoff's current law at node V2. After applying Kirchhoff's current law, we can write IN is equal to IF plus IB, that is, sum of incoming current is equal to the sum of outgoing current. At node V2, incoming current is IN and outgoing currents are IF and IB. As in the case of op-amp, its internal input resistance is very high, so that's why we can neglect its bias current, that is input bias current IB. Therefore, we can write IN is equal to IF. That is, IN can be represented in terms of voltage and resistances. How it can be represented? Say, this one is your resistance R1 and Vin is the voltage across its one terminal, and V2 is the voltage across another terminal, and current flowing through R1 resistance is IN. How we can write the expression for IN in terms of Vin and V2? That is, IN can be written as higher potential, that is Vin, minus lower potential divided by resistance R1. So here we have replaced the expression of IN with Vin minus V2 upon R1. Similarly, we can write the expression for IF. How we can write in the case of IF? here potential is V2, on the another terminal potential is V0, so we can write V2 minus V0 divided by RF. However, as we know, V1 minus V2 is equal to V0 upon A. Here A represents open loop voltage gain. As we know, the output voltage is directly proportional to the difference between the voltages across its two input terminals, that is inverting and non-inverting. So V0 is directly proportional to the difference of V1 minus V2. After removing this sign of proportionality, V0 can be represented as A into V1 minus V2. So from this expression you can write V1 minus V2 is equal to V0 upon A. Since V1 is directly connected to ground potential, that is 0 volt, so V1 can be put 0 volt in this expression, and we can get V2 as V0 upon A into negative sign, and substitute the value of V2 in equation 2. We get V in as such. After replacing V2 with negative V0 upon A, you will get plus V0 upon A divided by R1 as such, then is equal to, here also V2 can be replaced as minus V0 upon A minus as such V0 as such divided by RF. Now we have to rearrange this equation so that we can find out the expression for V out by V in. This expression is nothing but represents a differential voltage gain. To calculate this, we can cross multiply these terms. So RF will be multiplied to this factor and R1 will be multiplied to this factor. And after that, you can write RF V in plus RF by A into V0 is equal to, you can write minus V0 upon A into R1 minus V0 into R1. Now taking output terms, that is terms containing with V0 on the one side, you can write RF by A V0 plus, taking this side, V0 by A into R1 plus V0 R1 is equal to, taking this term outside, minus RF into V in. From this expression you can find the common value, that is V0, and after taking LCM you will get, and taking A outside, RF plus R1 plus A into R1 is equal to minus RF into V in. Now from this expression, calculating the ratio of V0 upon V in, and after rearranging this expression, you will get V naught upon V in as minus A into RF divided by R1 plus RF plus AR. This expression is referred as a exact differential gain or gain with feedback for the non-inverting configuration of op-amp. So this negative sign in the equation indicates that input and output signals are out of phase by 180 degree. So we will get phase inversion of 180 degree. So in fact, this is because in this configuration, that is in inverting configuration, due to this phase inversion, this configuration is referred as a inverting amplifier with feedback. This configuration or this arrangement is also referred as voltage shunt feedback amplifier. You may refer it as a voltage shunt feedback amplifier, or either you can refer it as a closed loop inverting amplifier. Since its internal gain A is very large, ideally infinite, so that's why the term AR1 is very much greater as compared to the sum of R1 and RF. This means the equation 3 can be rewritten as AF is equal to V naught upon V in is equal to, see, if we neglect this term, in reference to AR1, then A will be cancelled out and you will get minus RF by R1. So this is referred as a ideal gain of inverting amplifier with feedback. This equation shows the gain of amplifier is set by selecting the ratio of feedback resistors RF and input resistor R1. So you can say in this case the gain can be controlled by varying the value of feedback resistance RF and R1. So the ratio can be set to any value even less than 1. So let us now rewrite the equation 3 in feedback form of equation. So to write it in feedback form, let's see. Let's see the equation 3 again. In this equation, the resultant was ARF divided by R1 plus RF plus AR1, and there was a negative sign also. So we have to divide equation R3 by R1 plus RF. You can say multiplied and divide by R1 plus RF. And you can write the expression for this, that is ARF upon R1 plus RF divided by A. You can write the expression for feedback gain minus ARF upon R1 plus RF divided by R1 plus RF plus ARF divided by R1 plus RF. Now again rearranging the terms, numerator as such. In the case of denominator, you can write it after splitting into two terms, so that we can cancel these terms. It comes out to be 1. So you can write AF is equal to V naught upon V in is equal to minus A into RF upon R1 plus RF divided by 1 plus A RF upon R1 plus RF. Now you can say this expression is K, and this expression represents your feedback factor, that is B. So accordingly you can write AF is equal to V naught upon V in is equal to minus ARK upon 1 plus AB, where K is voltage attenuation factor and B represents the feedback factor. So we can conclude, in addition to phase inversion, that is negative sign, the closed loop gain of inverting amplifier is K times the closed loop gain of non-inverting amplifier, where K is less than 1. The gain of non-inverting amplifier was 1 upon the gain of non-inverting amplifier was A upon 1 plus AB. So you can compare these two expressions. There is a negative sign, another term is the K, where K is less than 1. So we can say closed loop gain of inverting amplifier is K times the closed loop gain of non-inverting amplifier. So the same can be represented with the help of block diagram, whereas in the forward path there is a block of value K, another is value of B. In feedback there is a feedback factor, that is B. Output voltage is V naught, input voltage is represented as V in, and there is a feedback signal using this block, that is VF, and there is a summing point. This one is a basically voltage summing junction as a model for current summing. Now we are going to discuss two special case of inverting amplifiers. One special case is current to voltage converter, that is its output voltage will be proportional to the input current. That is, after minor modification you can achieve V naught is equal to minus A in into RF. How we can achieve this? For this we have to replace these two components, that is V in and R1, by a current source of I in. If we replace these two components with the current source, you will get a current to voltage converter. Another special case is inverter. How we can define inverter? In the case of inverter, output signal is in equal magnitude but opposite in phase to that of input signal. So we can mathematically write it as V naught is equal to minus V in. For this we have to kept R1 is same as RF, because as we know its gain is minus RF upon R1. Gain is nothing but the ratio of output upon input. If we kept these two resistances of same value, then output voltage will be, you can see from this expression, the output voltage will be equal to the negative of input voltage. That is, magnitude is same but the sign means there is a 180 phase difference. So in this way we can use inverting amplifier as a inverter. So that was all about your inverting amplifier. Next time we will discuss another application of op amp. Thank you all.